Imagine you're a detective. Every new clue changes what you believe. Doctors do the same thing, weather forecasters do it. Spam filters do it. Even AI models do it. Whenever new evidence appears, your probability should change. Bayes' theorem tells us exactly how to update it. Last episode, we learned conditional probability. We asked questions like, what's the probability of A given B? That was already powerful. But Bayes' theorem asks something even more interesting. What if we know B happened, and now we want to reverse the question? Can we go backwards? Surprisingly, yes. And that's exactly what Bayes' theorem lets us do. Imagine you're solving a mystery. At first, you think one suspect has only a 20% chance of being guilty. Then a fingerprint is discovered. Now your confidence increases. Then camera footage appears. Now you're even more confident. Notice something, you never changed the evidence. You changed your belief because of the evidence. That's Bayesian thinking. Here's one of the most famous examples. Suppose a disease is extremely rare. Only 1% of people have it. Now a patient tests positive. Does that mean they definitely have the disease? Most people immediately say yes, but that's often wrong. Because we also need to know something else. How accurate is the test? Bayes' theorem combines both pieces of information, how common the disease is and how reliable the evidence is. Only then can we update our probability correctly. Think of Bayes' theorem as two moments, before evidence and after evidence. Before the test, this disease only affects 1% of people. That's our starting belief. After a positive test, once we account for both how rare the disease is and how reliable the test is, that belief jumps to around 16%. Bayes' theorem tells us exactly how to move from one to the other. Don't worry, we're not memorizing this today. First, let's understand what every piece means. This equation simply answers one question: how should I update my belief after seeing new evidence? Every symbol already comes from ideas we've learned: conditional probability and evidence. So how can a conditional probability like P of a given B become its reverse, P of B given A? That's exactly what we'll uncover next. At the end of part 1, we learned something important. Bayes' theorem isn't really about mathematics. It's about changing your mind correctly. You start with an initial belief, then new evidence appears. And instead of guessing, you update that belief using probability. That's exactly what Bayes' theorem does. Let's read this equation like a sentence, not like mathematics. First, we begin with what we already believe. This is called the prior, our best estimate before seeing any new evidence. Next comes the evidence. We ask, if it were actually true, how likely would this evidence be? That's called the likelihood. Then we ask, how common is this evidence overall? This keeps our answer properly balanced. Finally, the result is called the posterior. It's simply your updated belief after seeing the evidence. Let's revisit our medical example with real numbers. Out of 100 people, only one actually has the disease. Even a very accurate test can occasionally produce false positives, so some of the 99 healthy people still test positive. When we run the real numbers through Bayes' theorem, a positive test only puts this patient's true probability of having the disease at around 16%. So seeing a positive result doesn't guarantee the disease. Without Bayes, our intuition is often wrong. This is exactly how many AI systems think. Before reading an email, a spam filter starts around 10%. Then it reads the first word, free. Its belief updates to about 31%. It reads another word, winner. Now it's around 73%. It reads, click here. Now it's over 95%. Every new piece of evidence changes the prediction. That's Bayesian thinking, and it's the foundation of the famous naive Bayes classifier. Bayes' theorem appears throughout AI. Spam filters, medical diagnosis, speech recognition, recommendation engines, robot localization. Whenever a model continuously updates its prediction as new information arrives, Bayesian reasoning is often happening behind the scenes. Let's summarize. Bayes starts with an initial belief. New evidence arrives. The belief gets updated. The result is called the posterior. Bayes' theorem tells us exactly how to perform that update. Bayes' theorem is mainly used to sort numbers or update probabilities after new evidence. Update probabilities after new evidence. What is the prior? Your belief before seeing new evidence. True or false? A positive medical test always means the patient has the disease. False. Here's the sentence to remember. Bayes' theorem doesn't predict the future. It updates what you believe after learning something new. Now that you understand Bayes' theorem, you're ready for one of the simplest and most elegant machine learning algorithms ever created. Naive Bayes. We'll see how this single equation becomes a surprisingly powerful AI classifier.